As it says, we're here to talk to you about a project called BIG today. What we're going to go over is the architecture, some details about the implementation, as well as a few really cool demos, and then wrap up with the current status and plans. So the mission of BIG as a software system is to define an architecture for creating, provisioning, and deploying and managing internet-scale .NET services. What we mean by that is services with millions to hundreds of millions of users, lots of simultaneous users, and lots of machines. And where we're focusing is on the layer between the applications and the OS and the device. Now, the device, a very common device, of course, the PC running Win2K, but a device can also be a switch, a router, a Cisco local director, as you'll see in our demo. And with that, let's get right into the meat of it, and Galen's going to come up and tell you about cluster management.
Service like, say, Hotmail, you've got 4,000 machines. Anything that's difficult to do on one machine at a time is going to be extremely difficult when you have 4,000 machines. And so fundamentally, we have to worry about how are you going to manage a single node in order to manage a cluster. Another aspect of managing one of these services, you need to be able to completely remotely administer the nodes. It's not uncommon for people to be hours, if not days, away from their hardware. Okay, so on hosting these large internet sites. Another fundamental feature that we look for in managing the single node is being able to manage through an IP-based network. When we talk with the web TV operators, their most expensive network ports in their service are their serial ports that plug into their machines so that they can do administrative functionality. More expensive than their 100 base T or anything else per port when you consider the switching cost. And so, and the final aspect that we look for in our in our management of a single node is that we need to be able to go from bare boxes to a deployed service as quickly as possible without human intervention. So as we started out in this project, one of the first pieces we built is this thing that we call the B monitor. And the B monitor is 64K compressed code. It fits in Flash. Initially, we put it in the boot ROM on the NICs. And it's basically a very small operating system. It has an IP stack. It supports UDP, DHCP, TFTP, and a proprietary management protocol that we call BMCP for the B monitor control protocol. The B monitor owns the NIC on the box that it sits on, and so it filters all network traffic, deciding which IP traffic, which traffic should go to the B monitor itself, and which traffic should go to whatever is running above it. And the very fundamental goal of the B monitor is it's always up and always manageable. So no matter what happens to that node, I should be able to come in over an IP network and connect to the B monitor and reclaim that node. So with that, I'm going to show you a demo of the B monitor and how we use it for a single node management. Now, as I mentioned, initially we had the B monitor in the boot ROM on the NICs. We've since moved the B monitor onto the motherboard flash, so it co-resides with the BIOS in the motherboard. And I'm going to boot up. Let me see. I'm going to take this screen and show you. I'm booting up one of my nodes with the B monitor. You'll notice that we changed the BIOS logo as the node comes up because we're in with the BIOS. We can do that. The node comes up, it goes out and requests an IP address, and it's now available. So beyond the basic BIOS boot, it takes about 3 seconds for the node to be available over the network so that I can issue command operations against it. Okay. Yeah, I can. And when I go back, let's see. There we go. Okay. And I'll do what I can for you there. I'm going to actually be flipping back and forth between slides. So one of the things that the B monitor does is when it comes up, it goes out and connects to the B monitor management service. And what I have here is a debug console that's letting me access the functionality of the management service. So this node that I just booted up is connected to the management service, and I can issue operations against it. So the B monitor, one of the basic functionalities is I can load programs on top of the B monitor to run. And for reference, we call these applications that we load on top of the beam monitor, we call them engines. Okay, so I'm going to load a basic engine on top of this node, issue a command. I'm going to load an HTTP web server, very simple web server. Okay, and it's up. I'll start a browser and connect to that node. Okay, and what just happened is I issued a command against the node telling it where to load the engine from. It went out through TFTP, brought in the engine, and the engine is now running on this node. And in this case, it's a very simple engine. It's a static HTTP web server. So it's just serving up this content directly out of RAM. Okay. I can also do other operations against the node. I can stop the engine, so it goes to the red light and then back to the yellow, it's ready. So I've stopped the engine. I can reboot the machine. I can reset the beam monitor. I can reflash the beam monitor. So remember, the beam monitor is in the flash on the motherboard, and I can actually upgrade to a new version of the beam monitor completely remotely. Okay. Now I'm going to load another engine on top of the beam monitor, and this engine is what we call the image loader. And so I should clarify. When we started out, we had a bare box that just had the beam monitor and flash. It had an empty hard disk drive. Okay, and what this image loader is going to do is going to put a copy of NT on that box. Okay, and it's started. So while it's going, this is where you on this side are disadvantaged. I'm going to flip. Actually, you're both disadvantaged. I'm going to flip back over to the slides and talk for a while. And I'm going to leave that up for a minute.
So Windows 2000 is how big is
the image that I'm bringing in? It's a 1.2 gigabyte image.
How fast will that move?
It's going to bring it down in this case in about 2.5 minutes. Okay. Yes, you can time it if you want to. If I have a full duplex network, it'll bring it down in 2 minutes. Okay. So inside the basic node over here we have the basic architecture, what the beam monitor looks like. So the beam monitor sits in ring 0. It owns the NIC. It has NIC drivers. It has a disk driver. It has a flash driver to talk to the motherboard flash. It also has packet filter, and which determines which packets go up through the beam monitor stack so I can issue BMCP commands against it and TFTP operations. The beam monitor also has a very primitive API that it exposes upward to engines. Okay, and the beam monitor's API is primitive in the sense that, for instance, the disk API is raw disk blocks. Okay, and the network API is raw frames and packets. Okay, so an engine like, for instance, the HTTP web server that I just showed you has to bring its own IP stack if it wants to be able to talk to the network. Okay, it's a very exokernel-esque architecture in that sense. Okay, and then again, I can issue all these basic operations that I enumerated against the node. Okay. Now, so the basic boot sequence is the beam monitor comes up, it requests a DHCP address from the management service. As part of that boot request, no, take back. Sorry. Okay. It then, once it's come up and booted up, it finds out where its management server is. It registers with the management service, and then I can issue BMCP commands against it. So I can issue, for instance, the load command to load the image load program or engine. So image load comes down, gets loaded on the box through TFTP, and then in this case, image load, what it's done is it's gone out and opened a TCP connection to another server, and it's bringing down this NT image, this Win2K image. And on this side, you can see it's brought in roughly 1 gigabyte, right, so far. Okay, so the image load is going to bring down this image. It's going to create a partition table. It's going to create a partition, and it's going to write the blocks for the file system image into that partition table, or into that partition. Now, the image that I'm bringing in is a sysprepped image. So what that means, it's been built, the file system has been pre-canned, and then I drop it onto a box, and once it's dropped on a box, in fact, I'm going to go over here and show you what's happening on the beam monitor node. So it's going to reboot. So what happens is I've written this file system onto the disk, and then I reboot the box, okay, and I reboot into NT, and so NT is this sysprepped NT image is going to go out. It's going to generate a new SID. It's going to generate a machine name. It's going to basically take that file system image and turn it into a working copy of NT. It takes about 30 seconds for the initial boot. It then takes roughly about 2 minutes to do the sysprep of that box. And then you do another reboot, which takes about 30 seconds. End to end, it's about 6 minutes. I'll get to that in a little more detail. Anyway, back to talking about the image that I brought down. What I brought down is a Win2K server image. It has the iBuySpy demo from the PDC, which is a very simple .NET application. So it has ASP Plus in the image. It has IIS. It has SQL. Okay. In addition, it has what we call the bmonitor shim. So it has a subset of the bmonitor functionality embedded inside of it, which is, it has the bmonitor packet filter, it has the bmonitor stack, and it has the BMCP implementation. Okay, so this node I can still manage it. Now, when we describe this bmonitor shim, you can either look at it as a terrible hack or a very pragmatic way to bring NT into the big management fold. Okay, just back over to the screen here. So the sysprep is doing its thing that it does. It's basically sysprep runs the last part of the setup operations. Okay. One thing that I should mention, or I like to mention because it's one of my favorite hacks in the system, you'll remember that the bmonitor sits in the flash. It's a ROM extension is the way that the BIOS sees it. And so it always comes up before the hard disk drives would boot, before the disk boot would take place. And so by default, if the drive's empty, the bmonitor just always comes up. And so then one question you might ask is, well, so how did we boot over to NT on this node after I loaded the image? What we do in this case is we write a special signature into the real-time clock alarm. And as the bmonitor starts to boot up in the boot, it looks, sees the signature, and erases the signature and steps out of the way so that the normal disk boot can take place. And that's how we boot into NT. One result of this is that anytime that box reboots, so say if NT crashes or the power goes off or anything else happens, it's going to boot back into the bmonitor. And if I want it to go into the NT install on that node, then I have to issue a command against it. Oh, and here's one of our favorite features of the sysprep image. We have to wait 15 seconds in case somebody on the machine wanted to hit a key. Anyway, so that's the part of that. So we're now doing the second reboot on this node, and I'll let it go ahead. While it's doing that, I'll talk about some of the basic metrics. So again, I mentioned the BIOS boot on these particular boxes. These are what our bricks look like that we use for our nodes. It's a P3 600. It's got 128 meg of RAM, a 30 gigabyte ID, a UDMA 66 drive, and basically the only thing we ever plug into these nodes is a power and a network cable. We have a lab full of them here in the building, and most of the nodes in that lab have never had a keyboard plugged into them, they've never had a video plugged into them, and they've never had a mouse plugged into them. Okay, that's what headless really means as far as we're concerned. Okay, so the basic BIOS boot takes about 9 seconds. The bmonitor takes roughly about 4 seconds, and then here you have the breakdown of the full sysprep operation. What I want you to walk away from this is, in roughly 6 seconds, under ideal conditions, which is you've got 100 megabit switched network things, 6 minutes, sorry. I have a real problem with orders of magnitude. So if I sound off by an order of magnitude, question me. Anyway, so roughly in 6 minutes, we go from a box that's got a completely empty hard disk drive to a running NT image with your application running on it. So in this case, it's almost done. In this case, what we boot up with is the iBuySpy demo with SQL running, with IIS running. Okay, so from naked machine to a running service in 6 seconds, a running node of a service in 6 seconds. Okay, 6 minutes, 6 minutes. There I go again, huh? I'm terrible. This is why I'm not in marketing or something like that, or maybe why I should be in marketing. So I'm going to hit refresh on my browser, and you see that I hit the exact same URL, only this time instead of my hokey static HTTP web server, it's from iBuySpy. Okay, and one of the other aspects of this node is that it has remember, I've got the B monitor shim in it, so I can still come back in and manage it from my debug console. So, for instance, I can tell the node reboot, okay, and you'll see that voila, it really did reboot, and it's going to come back up in the B monitor, and I can repurpose it to some other node in some other service in another 6 minutes. Questions?
If NT hangs blue screens, do you still have B monitor control?
So right now we have a hack, okay? And the way I'd start, so there's a couple of things you can imagine doing. So we have our own TCP, our own IP stack in the shim, and we have our own region of memory, okay? So there's a number of situations where NT could blue screen that we could still keep functioning, okay, and still be available. The most outside way you can do it is just hook the blue screen so it always reboots the box and goes back into the B monitor, okay? But it's not completely isolated, right? Because in this case, the B monitor is running with NT and ring 0, right? You could imagine doing something, not that I'm going to advocate this, because it's a very difficult thing to do. You could imagine doing something like VMware does, where you actually push NT out of ring 0, and then NT goes down and the B monitor is still up. Anyway, another question over here.
There's absolutely no authentication of the messages going
At the BMCP commands?
Yeah.
In this particular implementation, there is no authentication. We have an authentication architecture, and basically what it consists of is the box holds public keys. So it holds my public key. And so when I go to communicate with it, I do a challenge response. It sends me a random token. I, as the only holder of the corresponding private key, am the only one who can decode that token and give it back to the node. And it can verify the encrypted token with the non-encrypted token. And so it's pretty trivial to build a very secure authentication mechanism on it. One of the things we do not solve, I should mention here, is that what I just mentioned is how I can authenticate myself to the node. Okay. What we haven't solved is how does the node authenticate itself to me in return. And that's basically the secure boot problem, which we have people here in research, Paul England in particular, working on some ISO-X and some methods of how you might go about doing that. Okay. But, and the question there is, if you're running a service and you've got all these nodes, how likely is it that somebody's going to bring in a node that's foreign into your environment? Okay. Yes, David?
About doing a reboot, it looked like a hard reboot. From the ROM, that's all you can be able to do. Do you have a driver? I mean, is it a real reboot in terms of a soft shutdown?
Oh, a soft shutdown? We just haven't implemented it yet. I mean, it's because the shim's in ring 0, and it has access to the NT APIs, so it could make the appropriate calls into NT to say.
Are you exposed to the driver, a WDM style thing, so that someone could write at the user level interaction?
How about I'll hold that question 1 minute, and then I'm going to talk about where we're going with this. Yes, back here.
Yeah, so you mentioned that if you wanted a new service, you just have a whole new image, but can you partition things? So you get NT, then you put a new application on top of that?
You could if that's what you really wanted to do. Basically, one of the things you find if you go out and look at these web services is that every box has some subset of functionality, and every box is single function. One way I would address it is if I have nodes, like this node costs $990, okay? And if I can build nodes for a K, and I can put them into my service, and I can manage them, and if I have one node or 1,000 nodes, management is the same, then one really asks, do I really want to be sharing this node? And, maybe V2 somebody will want to do that, but V1 we're not concerned with it.
Does the architecture offer partitioning groups of nodes? Like for 1,000 nodes do this service and 1,000 nodes do this service? Okay.
Yeah. So one of the things I should mention is I talked about the packet filter. One of the reasons the packet filter is in there is we can completely virtualize the network environment that the node sees. Okay. So we can create VLANs around nodes and do all sorts of things like that. Okay. Let me go on. So, what? Oh, yeah. So I'm going to go back to 2 screens. Right? That's what you're telling me, Dennis? Okay. Okay, so that everybody can see. There's some serious problems with the B monitor as it's currently implemented. Okay. It has to have device drivers for the disk and for the NIC and for the motherboard, the flash. Okay. And those device drivers are not NT device drivers. They're not Win9X device drivers. It's a new device model. Okay, so we have currently one NIC implementation. We support the Intel Pro 100 chipset. We have one motherboard implementation. We support the Intel 810 chipset. And we have one disk chipset, one disk driver, which is IDE, okay, UDMA. So the serious question you'd ask is, well, if we're going to go forward and try to deploy this, are we really going to have to go create new drivers for all these different devices? Okay. Given that line of reasoning, we immediately thought, well, wouldn't it be nice if we could take everything out of NT? So what I want you to think about is the version of the B monitor I just showed you is a prototype, okay, and proves the basic characteristics of what you want in the B monitor. And now what we're in the process of doing is building an NT-based B monitor, okay? And the way to think of it is it's got the same basic characteristics of it comes up, it doesn't rely on disk, it's always available, et cetera, okay? And so our prototype NT-B monitor that we're building right now, it boots over network, and it runs exclusively out of RAM. So what I do is I bring down a very small NT image. It's 3 megabytes. Okay, and that wasn't an order of magnitude error when I just said that. Okay, it's 3 megabytes. Okay, and that it basically consists of NTOS, the IP stack, the disk drivers, and the NEC driver, and actually user mode support. And then we have a B monitor shim so the B monitor, we now bifurcate it. Part of it is in the packet drivers down underneath, along with underneath the NDISC stack, and part of it is up in user mode. So that gets back to David's question. And so so we can issue commands against it. Okay. And again, the idea is it filters the network traffic. It's always up, always available. Okay. So then the deployment of NT looks like I have a bare PC. So I should mention about PXE. So PXE is this boot ROM standard, and it's PC98. So basically, any machine that's been bought in the last couple of years has PXE in the boot ROM. If you go into BIOS, you can actually select from your boot device. You can select LAN, okay, and with that LAN, then we can bring in this NT image over from PXE. So the idea is you put in a bare box in. It has PXE enabled. It brings down the NT B monitor, which is the NT kernel with our BMSS service running above it. And then I can load engines on top of it. So an engine might be an NT image loader, which I bring in across the net, and I write down a disk image onto that net, and then I can reboot the box to that NT that's running off the disk. Okay. And so the deployment looks like this. As I mentioned, we do the PXE startup. There's an initial step, which is we use multicast TFTP to bring in startrom.com, which is this 32K loader that then makes another MTFTP request to bring in the NT image. And this NT, the B monitor NT image, okay? And that consists of NT loader, the basic NT loader binary, and tacked onto the end of it is a RAM file system. It's a compressed RAM file system. And so then that image, which is about 3 meg, gets loaded on the box. The boot turns over to NT loader, and NT loader then pulls all the rest of the files that it needs out of this RAM file system. And we actually have that file system implemented, and we're booting it right now in our development environment. Anyway, and then you could then issue BMCP commands against that. And what we'd envision going forward is actually doing something like bringing in an image, a 1.2 gigabyte NT image, is you would use something like FCAS, which is the broadcast technology developed by Jim Gemmell down at BARC, so that you can minimize your bandwidth usage when you're redeploying hundreds of machines, for instance. Okay. So I've talked about how I hope what you got at this point is a basic feeling of, yeah, we can manage a single node and we can do interesting operations against it, and no one ever has to go out and touch that box. They can just administrate it remotely. Well, the next question is, well, why should anybody have to administer that box at all, even remotely? Why can't we turn that over to software? And so the rest, now what we want to do is turn it over to Bob, and we're going to talk about how do we manage it from software instead of from people.
Is my mic on? Yes. Okay. What I'm going to describe is sort of the next layer of the architecture, which is how do you manage a large number of nodes in a sort of intentional way? You want it to do specific things. So the sort of inspiration for us is our diagrams like this. You've got, no, won't do that. This is like a picture of a sidewalk diagram, and you see these in a lot of different places within Microsoft, MSN, and they basically try to capture in a hand-drawn Visio diagram the structure of the large-scale application that is Sidewalk, and they detail all kinds of things like, you know, what kind of machine it is, what IP address that machine's been assigned, what software is going to load onto it, what disk partitions it has, how those disk partitions are used, who has administration permissions on those different partitions. And the problem with these diagrams are that they're hand-drawn diagrams and they quickly go out of date. And so they are of limited utility unless you're very vigilant about keeping them up to date. So the thought experiment is, well, what if we made this a live document? What if we made it a live document that you could program against, for example? Then, like, what would that give you? So I'm going to step you through a sort of a process of thoughts that we've had. One is we're going to take the individual components of this cluster of machines and we're going to categorize them. And we're going to replace the multitude of machines by single nodes in our abstraction here. One of the nice things about these web services is that they tend to have a fairly small number of these nodes that are differentiated, right? Hotmail has probably less than a dozen different node types, right? And yet they have 4,000 machines. So there's a lot of replication going on. Then we'd also like to capture the interconnect topology between these machines. And that basically describes, gee, who can talk to who, what protocols are they using, et cetera. We'll get into this in a lot greater detail later. We call this thing the scale invariant service definition. What it is an attempt to describe the service where we've removed all of the scale out of it. Okay? What we're going to do with that is we're going to apply policy to it, what we call policy scripts to it, to govern the growth and management of this service. Scale invariance allows us to think about the service at any scale, right? So it could start out with 10 machines. It could end up with 4,000 machines. And our hope is that if you've designed a good scalable architecture, and we can't do that for you, that managing that architecture across all of the scales that you're trying to achieve can be done with a single model. And then, so to go back to the picture we saw first, here's how we're going to get it. We're going to take this scale invariant description, and we're going to use it to guide the allocation of nodes and the management of those nodes over time. And so we'll end up mapping nodes back into these component types. So a key point about this scale invariant model is that what we're trying to do is provide a framework to author management policy as code. This is one of the big problems that you see in large websites, is that they have operations guys who have operations books, and when things go wrong or when they want to do things, they're doing things with a combination of, say, Perl scripts, things in people's brains, and their own actions, right? The problem with that is multifold. One is there's no common framework for authoring these kinds of policies, these operations policies. Secondly, a lot of the information about the app is in the heads of operators. So if you lose one of those guys, you have a really big problem. And it turns out that the really good ones don't stick around for very long. We talked to David Cole about this, and that's one of his key problems in MSN today. And the third is that because each system is different, you can't take expertise from one property and translate it to another property, right? So we would like to approach this problem in two ways. One is we'd like to provide the framework that allows a common base to capture knowledge. Secondly, we'd like to embed as much of that operations policy into code so that it's out of the person's brain. And thirdly, we'd love it if we could create reusable policies so that a policy about, say, how you grow front ends or you partition back ends or something, to the extent possible, can be reused by other properties. What you see today at MSN is they reinvent everything over and over and over and over and over again, and that's because there's not a common reuse strategy for those things. So that's, I'm going to hand over to Bassam Tabara, who's going to give you a demo of how we think we're going to do this. But maybe I should ask if there are any questions about my vague. Yeah.
The model is flat. So, for example, if I needed to partition my FTP servers a certain way, I would have to create top-level flavors of FTP server, right? I don't have inherited policies that would go down and say, yes, it's an FTP server, but it only serves this partition of files, or this set of
no, we in our vague diagram, we didn't show that we have, for example, compound components. You can hierarchically decompose your service into reusable component chunks, for example. So if you want to have multiple instances of a TFTP server, yeah, absolutely, you can do that.
They would share whatever policies were in common. They would share.
Where
they diverge, they would be unique.
Yes, yeah, and uniqueness is either there's different behavior running on the node, or they're at a different part in the service topology. Or they're, yeah.
Okay. All right.
Is this better? Okay, so I thought the best way to actually show you what the big framework is, the big platform is, to actually show a demo. And so we took the iBuySpy demo from the PDC. I'm sure most of you guys are familiar with that. It basically is a simple e-commerce type website. It's an excellent demonstration of what the .NET framework offers. It's really easy to author these things in ASP+ and C# and use ADO+ and talk to the SQL backends and do all that good stuff. And it's really powerful. It uses standard web tricks that, like client-side cookies, and they use middle-tier objects and all the good stuff that Microsoft's been telling everyone. So that's all good. What it's lacking, though, is when you actually want to take this and deploy it in a .com type environment. What do you do when you want to take this and scale it to something like Hotmail scale, and you have 4,000 computers, and you want to manage and deploy iBuySpy on these computers? How big of an operation staff do you need? How many people do you hire? Do you go off and write these manuals and troubleshooting manuals and how to handle failures on these applications? There is no framework that brings this whole thing together, and we don't have anything. Microsoft doesn't have anything to offer in this area. So we're hoping that we could show you at least a vision and a spirit of what we're thinking about and what Big is thinking about in this area. So to make this a more representative demo of what a .com does, we actually took iBuySpy and turned it into iBigBuySpy. And it's iBigBuySpy is basically, we basically added load balancing in front of the front ends, TCP load balancing. We also changed the front ends and the back ends, SQL and the front ends, to slightly to talk to the big management service that you've been hearing about. I won't really go into all the details of what that means, but hopefully you'll hear little sporadic things here and there about what we're doing. But the front ends keep basically through our node coordination protocols. The front ends keep track of how many backends there are, and they can actually do things like distribute their load across the backends. We also added policy, and you'll see this is the equivalent of the operations staff running around and all the different troubleshooting manuals, and we want to capture all that in code. And as you'll see snippets of that later on, and you'll see it actually running. So we think this is a little better representation of a .com environment. For this demo today, we've skipped on the hashing part, hashing the backends, and we're just going to show you the distributing the load across a single SQL database, and that's read-only for now. So what do we mean by when we say a service? You keep hearing us referring to a service in Big. When we say a service, we actually mean a service. In our definition of service includes the actual nodes that actually run the application code. So the ASP plus, the front ends, the SQL backends, all that stuff. All these nodes are included. The network topology between them, but also all the operation processes and management policies that, as Bob mentioned, are captured today in people's heads or one-off Perl scripts or troubleshooting manuals that these operators live by. We capture all these qualities in what we call the Big service definition. And you saw the example of Sidewalk was an example of one. It's important to note that this service definition is scale invariant. So it's independent of scale. And in fact, nowhere in this, I'll show you how we actually create one of these. Nowhere in there do we talk about the actual machines. That's a separate independent process that run this. And it's also not tied to a specific deployment. So when we're actually sitting down and creating one of these services, we're not thinking about, this is in Canyon Park and it's going to be on these 50 machines. No, this is done, the provisioning is done independently of the creation of the service or the service definition. And we think that's actually very important. So what is a service definition? I'll talk a little about the different parts in the service definition. Service definition is primarily made up of these things we call components. And components are a complete description of all the code that will ultimately run on a physical node on that machine. So basically, it's, in our example, the beam article, it'll be the name of the image that we download, the NT image that we download and we provision the box with. But it also can include any kind of specialization for that machine. Components also describe the type of node that they will like to be deployed on. For example, so if we wanted this to be on a special box that has to be a box in a secure cage, et cetera, you notify with this thing we call a node type, which is associated with every component in the service definition. Components also have one or more ports, which are their external interfaces into the component. This is how you actually communicate with components, is through their ports. Ports are typed by the network protocol and the role they play within this protocol. So, for example, the iBuySpy front end has an HTTP server port. And then there are wires, which represent communications between ports and different components. And wires themselves are typed by the network protocol. And then it's also important to reemphasize that the external interface into a component is through its ports. We never refer, for communication purposes, we never refer to a component by its component ID. It always goes through ports. So without further ado, I'll actually switch. Actually, I can probably switch both screens. So I'm going to show you how to actually create a service definition for iBigBySpy. What you're looking at here is our simple service definition tool that we've prototyped. It's an extension, it's a VB extension to Visio, and it kind of provides a graphical way of describing these components, ports, and wires, and connecting them up in interesting ways. So I will, on the left here, you'll see that there's a bunch of shapes that are in this component stencil that we've made specifically for this demo. So you'll see the policy, the product database, the front ends, and the load balancer components. And you can actually create new components and attach wires. These ones have been just pre-canned for this demo. So basically what I'm going to do is just drag and drop these components. So there's the product database. There's the front ends. Here's the load balancer. And then there's the policy And these have been configured so you don't have to actually wade through all of this. The name of the image that will actually ultimately run on the boxes have been preset on all these components. You can go through dialog boxes and set these things on each component. This is just a prototype tool that we wanted to show you, but you can get an idea. You can kind of get an idea of what's going on here. So I'm going to actually wire these up. So I'm going to wire the local director telnet port to the policy engine. I'm going to wire the HTTP ports, and I'm going to wire the TDS ports, which the SQL backend, and since this all lives in this thing called on an outer service called Big Buy Spy. And then finally, I'm going to externalize this port so that the outside world can see it. Oops. And then the last thing I'm going to do is actually compile and save this thing into the big management service. So I've now created a new service definition. By hitting save, I've told the big management service about this new service definition. I told about all the components and ports. And in ways, I've defined a schema for this iBig by Spy. So that's this part. Let's switch back to the slides. So you'll see how this service definition, we're going to take this service definition and we're going to take it and deploy it on the number of machines we have in the lab. And I'll show you actually how that's done through policy and how this service definition that you've seen acts as a namespace for that policy. So when you want to create a new front end, you actually refer to the component in the service definition that's called the front end, and you say, I want a new instance of those. And the big management service actually takes care of what that means and how the deployment happens. So you'll see a little bit of that as we move on. Now, as I said, provisioning is a separate effort. Nowhere in when I created this service definition you just saw me create, nowhere in it did I say how many nodes I have or where these machines go and how they're connected and all of that. We actually want this to be a separate process so that you can actually take something like a generic service definition of a service and deploy it in different places. And we believe provisioning is done by this resource manager. And so a resource manager is basically a thing that keeps track of all the nodes in a data center, for example. So it keeps track of all the machines in the data center, but it also includes network hardware. So local directories, switches, and routers. Everything gets listed as a node, and they're all integral part of the whole service. Every node in the resource manager is associated with a node type, and that node type actually ties it back. It's our link back into the service definition model. So when a component had, said I want to be deployed on, I am a front end box and I need this kind of machine. That's the mapping that we actually hooks both service definition and the actual nodes in the resource manager. But resource manager also have a node type associated with them, which kind of could give more context. For example, this is a machine in an ultra secure cage, or this is a machine that has really fast or has access to the outside world, has access to the internet. As opposed to a private net internally. So we haven't done, so far this has been, the resource manager doesn't keep track of the network topology, the physical network topology. And we're actually working on that now. But the demo you're seeing now, it's just basically a flat list of nodes that have all these properties. So now that I have a service definition and I have provisioned a bunch of machines, and in this case we've done 20 machines. We have 20 machines assigned for iBig by Spy, registered with the resource manager that are running in our lab. So now I have the service, I have the machines. How do I actually bring them together? How do I actually deploy iBig by Spy? And today that's actually done by a number of people going there, installing machines and bringing them up and bringing the service up. We also, in Big, we envision that would be totally done automatically by code. And then we call this, the constructor policy. This is kind of, if you think of iBig by Spy as a big service, then this is the constructor for the service. This is the thing that will bring it up, and it's the initial condition with the initial condition. So basically, the operation that the constructor policy does is it allocates nodes from a resource manager and then instantiates them by going through our big management service. And we keep track, the big management service keeps track of this instantiation, keeps track of the mapping between the physical and back into the service definition, which is a logical space. So I'll talk a little about mapping. So we said a component provides all the information that we need. So that's the name of the image, what we need to tell the B monitor on these boxes to deploy this image. So when you see a component, what we store in our state tracking database, when you see a component, we store all the instances that are associated with that component. So when you say there's a front end, when there's the iBig by SPI front end, we keep track of all the nodes that have been allocated and made front ends, right? Repurposed to become these front ends. In the same way, wires in the logical space keep track of a possible set of communications, allowable mesh of communications in the physical world. So if there was a specific physical topology, network topology, or communication topology, we will keep track of that from the logical space by this wire identity. And in the same way, ports let us track all these service access points on the individual instances of the machines. So all that information, all that accounting is actually maintained by the big management service. And interestingly enough, can be used for very interesting purposes by policy. So you could ask questions like, where are my front end machines? Or you can actually go, given an IP address, you can find out where its place is in this service definition model and be able to do very interesting things. And it's also, like Bob said earlier, there's a huge order of magnitude difference here between the number of components in the service definition model and the physical instances that you get deployed. So Hotmail is the example where they have, I think, 7 different components in the logical space, and they have 4,000, 4,500 computers that are actually running Hotmail. So the number is very small. They can actually do some in-string reasoning on top of that. So I'm going to show you what it takes to deploy our service definition. So we've written a little simple policy for iBig by SPI. This is all done in C#. In the .NET program, it's a pretty simple app that's talking to the management service and talking to the resource managers and doing the allocation and instantiating these machines through the mechanisms you saw Galen demonstrate and through some of our big management service API, which I really will not go into much detail. The constructor policy that we authored is pretty simple. We're going to start up the Cisco local director, and we talk to the Cisco local director through a proxy. So we wrote a little object model in front of the Cisco local director that talks telnet to the Cisco box and actually can configure the Cisco box through our policy code. Our policy is pretty simple. We're going to start up the Cisco local director. We're going to start up 2 front ends and a back end. And as these nodes come up, you'll see I'll show you what actually goes on. How do I? Okay, I'm going to close this guy here. This is the same debugging console that Galen showed you earlier. So there's about 20 machines that we have in the lab. They're all running the B monitor. They're all ready. I don't want all of you to sit through 6 minutes or 7 minutes of downloading NT and booting it. So what I've done is actually pre-cached the images on the disk, and they've gone through their initial boots. And all that I have to do, the command that I send right now is the last reboot. So you guys don't have to wait through this. In a real environment, this would involve a 7-minute download and then running of the image. I'm going to start up another kind of debugging console, where the policy can spit out its thread of execution and show you kind of what it's doing to kind of give you an idea of what's going on. And then what I'll do is start my policy engine. And you'll see it'll start spitting out a message and telling us what it's doing. So in this case, a policy came up. It connected to the resource manager, connected to the big management service, and now it actually has kind of the things it needs to actually start deploying instances of these components. What at first it is actually talk to the Cisco local director. Cisco reports that it's up, so the proxy is initialized. It opened a connection to the Cisco box. It came up, and then the policy engine allocated 2 nodes, actually 3 nodes in this case, or 4 if you include the Cisco box, and instantiated them. It basically told the management service, here's a node, here's an IP address of a node I just allocated from a resource manager. I want a new component out of the service definition model. In this case, I want 2 new front ends and I want a back end box. And all the mechanics of what happens there, how we issue BMCPE commands to the B monitor boxes has been encapsulated inside the big management service. So you'll see these boxes boot up. You'll see the name change going on. This means our B monitor shim just came up, and it displays the name of the image. NT is actually still booting at this point. The front end, the code on the front end boxes and on the SQL boxes, we have when they come up, they register themselves with the big management service. So they say, I'm a new, big management service invokes or creates a new front end or a new box, and then creates a new SQL backend. When they come up, they say, oh, here, I'm up. I am a new instance. I am a new component instance. And that actually that's how we keep track of these instances in our state tracking database. They also register their ports. They say, well, for example, when the front end comes up, it comes up, but when ASP is done and we've done all our initialization on that machine, we want to expose the HTTP port. So what it does is it actually tells the management service, I now have a new instance of this HTTP port that's in the service model. So that policy can actually look at that and decide to connect these machines up or send in new commands or do a bunch of interesting operations. So in this case, what we've done is you'll see the I'm up messages that came up from the different machines. So node 13, which is the second node, came up, and it declared itself as ready. And it did that by actually registering its SAP. It's registering its HTTP SAP, which is the service access point, an instance of a port. And similarly, the backend, the SQL boxes came up. And then they were both told through our coordination protocol, when they both came up, policy instructed both of them that told the front end there is now a backend you can talk to. This is all done through our management APIs. And then they both know each other now. So what happened is the front end added the backend to its list of SQL databases it can render from. And the policy detected the new front ends and added them in the Cisco local directory group. So we can load balance across the front ends. This is all done by this piece of code. What I'll do is I will actually switch to another session here. And now that iBig by Spy is up, I can actually go in and show you what it's doing. So this IP address that I'm hitting is the front end of the Cisco local director. So we'll actually get load balancing across this. And as you see, the service is up. You'll see on the top left corner in red, right above the hat, the IP address of the front end machine that's actually rendering this page. And you'll see also the back end that it's talking to render this page. And then a count of how many backends we have. So the previous page I just showed you was on number 12, and now we switched to 13. So you'll see as I walk through the site, you'll see that the local director is load balancing across the site, and then we're just hitting the one database right now. So that's deployment. I'm going to show you a little snippet of code from so there's a little snippet of code in the policy the constructor policy. And basically, it's as simple as you see. You call a resource manager through our API, you allocate a node, and then you give that IP address of the allocated node to the management service, and you ask it to instantiate an instance of component front end, which in this case was the component in the service definition model. And then behind the scenes, we're doing all the mechanisms to actually bring that box up. And the management service also will fire events when certain things happen. So when a front end shows up, it fires an event that says there's a new component instance, or when a SAP is registered, the policy can track these events and do some interesting things. So in this case, we look for the HTTP port on the front ends, and we take that event, and we actually add that box to the local director load balancing list. So what's the big deal about all this? Well, we've seen how actually we've taken a service definition model that was written not to a specific deployment, and it's scale invariant. We took a description of the number of machines in the resource manager, and we took some code written on the top of our framework that actually binds the two. Basically, takes the service definition and creates instances of it in the physical space. We've seen how this point constructor created the initial condition, and in this case, it was 2 front end, the local director box, and the back end. And this is all done through the use of our resource manager, our state tracking database, and our big management service. So now that the service is up, it's running, things are smooth. Well, then this is the complete next stage of the service's life starts. How do you keep managing this thing? How do you grow it when there's demand, when there's more demand? How do you do even mundane management, like doing nightly backups or running batch processes, offline processes, or even dealing with failures? What happens when a front end just blows up? What do I do? How do I keep track of all this stuff? Today, as you all know, this is done by a number of people running around and like with their heads cut off and just going crazy, handling case by case basis. And so we want to do this all in code. We want to do this all in software, and we want to bring it all together on top of this same framework. And there's a number of advantages for doing that. If you actually get to a point where you have a framework for doing this, then you can actually imagine scenarios where you can reuse some of these policies, failure policies or partitioning policies, or how do I, this code that you saw, to actually add things into a load balancing group. How many times do we have to write that over and over again in like either Perl scripts or people doing it manually? So management involves a lot of things. We're going to show you one example in this demo. We're going to show you growth. So imagine, iBig by SPY is super popular, and a bunch of people just start banging on this site. What do we do? How do we grow this site? How do we allocate our nodes? We have 20 nodes, which we've used 3. How does this thing grow? So in this demo, we've written a very simple growth policy. And you can imagine writing much more complicated ones, even ones that negotiate more resources with the resource manager or any other service. But in this simple example, what we've done is every time we've monitored, we're looking at CPU load, CPU performance counters through WMI. The policy is monitoring the CPU performance counters on the front-end boxes and on the back-end boxes. If it goes about a certain threshold, we blindly create new machines. And if we run out of resources, tough. So that's the simple policy that you're seeing today. So if I switch back, what I'm going to do is start the Microsoft Web Application Stress tool. And we've written a simple stress that will actually hit the pages in random order and do all sorts of interesting stuff on top of this website. As I'm going to start it, actually, one more thing. Let me switch back. And start perfmon, so you can actually get a look at what's actually happening. So the window to the left shows the number, the bar in red shows the number of front ends that are currently running. Bar in green shows the number of SQL backends that are currently running. And then the other one is the CPU. We've picked 2. In this example, we picked node 12 and node 27. We're showing you CPU, the CPU performance counter on these boxes. And I think I had the threshold set to something pretty low because we couldn't simulate much load on this machine. So I think it's like 50% or 60% or something. So I'll switch back and start the stress tool. And as it loads up, you'll actually start seeing the load increasing on these machines. And then the policy will get all these overload events. Is it going? Let's add more load. Or click through this and maybe you'll... Or refresh. Ever done that on a website? Huh. All right, just bear with me a second. Yeah. Ooh. Okay. This is the first time it failed. Done this demo about 7 times. Okay. Let's see if we can get. What's that? For what?
This one, just go ahead. It's not doing what it's
Well, bummer.
Yeah, that's what you said.
Yeah.
Just tell them what happened.
Okay, so I don't know what's going on, but basically what you would have seen is the WMI events would have fired on the machines as soon as the load hit, and you see the threshold. The WMI events would have fired on the machine, and the policy would have tracked that event and would have said, okay, well, there's some new load, and what it does is it actually starts creating these front ends, and you'll see the red lights of the machines rebooting, and then coming back online, and then the more front ends come up, then you have more load they're putting on the back ends, and the back ends start coming up, and then it's just a cycle, and then we run out of resources, so no more boxes come up. I'm really bummed. This is actually a cool part of the demo. What's that?
Is there a way to provide a backup managing machine?
Sorry, I can't hear you. Speak up.
The machine that manages the other nodes, is
Yeah.
there a way to provide a backup for that or multiple?
Yeah. Actually, so what we're doing right now is we only have one service, right? The one single machine, and that's for our prototype. This is a single point of failure, and you actually have to do your work in scaling that thing and making it reliable and actually having like a backup for it or a failover for it. Yeah, totally. In fact, we're even thinking about Bob's autonomous view of the world is actually what if every machine had a little piece of that on it so that you never fail, or your fail is determined by the number of machines you have. Okay, so I'm going to skip this part and then switch back to slides. So here's a little snippet of code that didn't run, but this is what it should have done. We would have got the WMI event saying the CPU overload. WMI will tell us about the IP address. It doesn't know anything about a service definition model or anything. So this is actually the first time you'll see us use the management service for introspection. So we're actually taking this IP address and going, well, what is this thing? I just got an event. I don't know. It's a CPU overload. I don't know if it's a front end or a back end. So using our management service, we go back with this IP address and we ask, look this up for me. What is it? And if it's a front end, then we're going to create a new front end. If it's a back end, we'll create a new back end. Or, as you can imagine, you can do more interesting policy here. But and if it's neither, then we'll fail. Yeah.
So your policy is procedural.
Yes.
You don't have any You don't have a declarative.
No. Right now it's
actually statically analyzed.
It's imperative code at this point. And we've actually been thinking a lot about how to make it declarative, including modeling things through BitStalk or slang and bang, and defining a model for policy. But what we're showing now is the imperative version. But yeah, the more declarative is, the more you can actually reason over what it's doing and actually be able to reason over policy.
Where it doesn't cover the space of need.
I'm sorry?
Find places where it doesn't cover the space of need.
That's right. That's exactly right.
Conflicted rules firing at the same time.
That's exactly right. And you can imagine things like you also want to keep audit trails and you want to keep what's going on. And there's a lot of things. This is a lot of things we have to actually get running. But so what you've seen or not seen is a system where it can deploy itself, it can manage itself. We hope we make you believe that it actually can deploy and manage itself on a framework that could be used in a number of different services. These are actually services that we want people to use, like the resource manager or the management service itself. And since it is code, since it's it's not a number of manuals or a number of people running around. So it is code. You can imagine opportunities for actually modularizing this code and actually reusing parts of it. So, for example, if you wrote a policy that handles CPU overload on machines and grows them in a way, you can actually imagine taking that policy and reusing it in different places. And this could become a big asset for Microsoft as well, because it's the smarts of operations that we can capture on top of this framework. So that's okay. Sorry. So basically, that's our demo. You had a question?
Yeah. What's the kind of smallest system that a developer writing these rules can use to test or debug what they've just written?
Using for the system?
Do they have to have?
Well, so what you need today is you can actually run this all in one box if you wanted to. I mean, the management service is a SQL database with our API sitting in front of that. But this is.
There's no way to simulate a Cisco router without actually having one. Not today.
The one we have actually talks to the box itself, and that's probably what happened here. We lost network. So yeah, we haven't done. But you can actually simulation is a very interesting topic. I mean, if you have a service definition model and you can actually instrument what happens, or have a model for what happens on these components as things progress. It's very interesting to think about simulation models on top of this framework and actually see what happens when on load or on catastrophic failures, and be able to debug your policy. But any other questions? Yeah.
It's bothered me that Windows isn't structured at all to do this kind of work, and you guys are working around it. I would like to ask a question of all of you. If the gods of Windows 2000 came to you and said you can have any 3 things you want, what would they be from Windows? Actually, what have you run into that is really, really, really stopping?
One of the things that we'll get to in the later slides is where we are and where we're going. And one of the things we're going towards is some offsites with the Windows team. Later slides are going to go into where we are and
yeah, we're going to actually talk. Galen talked a little about how we're actually taking the B monitor and taking some of our thoughts and transition over into Windows 2000 or Whistler in this case. So Dennis will actually touch up on that later on. I'm going to pass it back to you, Dennis. Or actually to Bob, sorry.
I'm going to give a very brief overview of sort of the architecture as we think about it. There are pieces here that we haven't done yet, and there are pieces here that you've seen in a demo that didn't quite work. But I'm just going to go through this hierarchy and give you a sense of what the story is. At the bottom layer of it, we have a set of what you might call appliance device drivers. We showed you the B monitor, which is controlling just generic PC-ish kinds of nodes. You saw an embryonic version of the load balancer device driver. And we've looked at switches, routers, and disk devices like SANs or NAS devices. The goal is to sort of abstract those with the Microsoft API so that we can build complex policies on top. So, for example, you saw explicit code in Bassam's demo where we were telling local director, that a new front end showed up. But there's not really a good reason why that can't be done in a more automated way. If you connect a local director via a wire to a front end, the semantics of the wire in some regards could be to keep the local director's, table of front ends in sync with what front ends are actually attached to the wire. So on top of that, we have a set of hardware definitions. What you've seen so far is the simple hardware inventory that we view as a flat space. Talking to people building large clusters, that's a very unacceptable solution. Topologies, network topologies, the physical topologies are often quite complex, and they want to be able to allocate and organize nodes according to the topology. So what we're working on right now is a definition model very similar to the logical model that captures the structure of the hardware topology. So, for example, in our example, we fix allocated front ends and back ends. Those often are associated with sort of topological characteristics of where the node is in the network. The demo covered most of this space. We have the instant state tracking, which is just what each node is doing at any given point in time, what state is it in, what SAPs or port instances it has registered, what wires it's connected to. The physical resource manager is the guy attached to the hardware topology. Another aspect of the physical resource manager that's interesting to us is we would like to do auto discovery of new nodes. You'd like to take a low-skilled technician, and he should be able to plug in a new computer into the cluster, and we should discover it automatically. They shouldn't have to enter anything into a database. They shouldn't have to do anything. Similarly, if they take one offline, we'd like to discover that as well. Our current thoughts are that's pretty easy to do with PCs. It's harder to do with switches. It's even harder to do with routers. So that's a pragmatic. It's like plug and play. We don't have plug and play for network components today. The coordinating primitives are, the way to think about those are, if you think about a wire, there's a set of changes going on in the wires. These service access points are appearing and disappearing, and there's a synchronization problem that you need to coordinate. So, for example, if a front end wants to go offline, it's important that the local director remove it from its load balancing group before it goes offline. So there's something akin to a two-phase commit where you say, I want to go offline, and everyone who might be affected by that says, it's okay for you to go offline, and then I go offline. And that way you can keep those things that need to be in sync to keep the consistency of the topology. And then the last thing is what we call the service definition model and the object model that supports that. And you saw that with Bassam writing code against it. And service definitions get turned into the object model by effectively injecting it into our what is today an SQL database. One point I should make, and we don't talk about it in this talk very much, is that the framework supports not only deploying a single service, but any number of services. So, and it can do so in a hierarchical way. So it's possible for us to model not only, say, Instant Messenger, but Passport and other services, and the fact that they may be co-located in a single center and that they're drawing on common resources. That's not something that MSN does today very much at all, but there's a lot of appeal to that, which is if I can reuse hardware across services, there's some benefits. If I can manage the hardware resources from a central place, there are benefits to that. So that's sort of the big picture. I'm going to hand it off to Dennis, who's going to give you our status and our future and stuff we're hoping to get from other people. Oops. Oh, no, wait. I have one more slide because I always... No, I don't. Sorry. I always think I forget a slide.
We took it away. So the big deal for us, what we've brought to the table in terms of offering a service, are three things. The B monitor, which lets you manage and purpose a node without any hands-on, anything from something that's already running to something that's hung. And as Galen noted, yes, you can hang something to the point where, given our current architecture, like if interrupts go away, we can't bring it back. The service definition model, which lets you create this scale and variant description of what a service should look like so that it can later be deployed. And then the big management service, which involves the policy, the database, all the pieces that will actually let you deploy, manage, and grow your service. So what I want to describe for you next is where we are with what we want to call version 1. We can drill down on some of the details, and that is necessary, and then the action items, how we're working with the other groups. What we want to do, and one of the reasons we are working towards a NT level B monitor, we don't want to be in the low-level support business where we're tracking each new motherboard chipset that Intel lets out and all the NIC card vendors. The Windows team is already pretty good at dealing with that. So we want to hand off support for a low-level driver to them, and towards that end, we've been prototyping the B monitor as using the NT kernel. The NT team also has people worrying about setup, sysprep, fusion, things that OEMs need to do to provision machines. We have a lot of the same sorts of needs. Right now, our image builder is a knowledgeable developer, one of 4 people on the team, who sits down with sysprep, carefully manages something, snaps it, freezes it, and then goes out to a FAT file system and captures the blocks. That won't scale very well. So we want to use something that will let us create images, probably tiered images, so that we have one version of NT Advanced, of Win2K Advanced Server that is then propagated across front ends, back ends, staging servers, etc. And then in order to test it, we can architect to our heart's content, but will this really work? The way we'll test it is we want to create something that we can deploy a scaled model of Hotmail, at least one other MSN property, and from talking to MSN, that's probably Passport, and then the MS Exchange server farm, so that we can manage our own Exchange servers. One of the reasons we like going after that is it demonstrates an enterprise level of NT servers without the internet involved. But also, Exchange has tools for repartitioning backends on the fly. We don't want to invent those tools, but we do want to have a way to test policy to manage that sort of thing. As Galen explained to you, our current status is the B monitor is burned into motherboard chip, burned into the flash on the motherboard. We're beyond. I actually need to update this. We're beyond investigating. Bassam and Galen have the code in place that actually lets us boot. And if you want to look at what it does in the debugger, you can see how far along we're coming in the boot of the NT kernel. But we still have some work to do to get that a little further. There's several groups, as you might imagine, that are interested in the ability to boot and provision machines. There's App Center, there's Data Center, the headless server team. There's our network solutions group who has to deal with this with customers all the time. So we're going to host an offsite. It's actually going to be in mid-January to talk about the needs of all these groups. So as we go to hand the stuff off to NT, it covers more than just what we need. That's where we were talking about, Dave, that I was going to get back to that for you. The installation, we don't want to be at the point where you need one image per component laboriously built by hand. We're already talking to Dave D'Souza and the Fusion team about how to deal with that. We're going to talk about those requirements at our offsite as well. For our devices, we have B monitor working for running computers in terms of the NDIS shim and also in terms of burning it into a type of computer in the motherboard. We're expanding on that using the kernel for broad NIC support. And we also want to expand or extend our health and monitoring functionality so we have a better idea of when a node appears to be online but it's really not responding. The Cisco Local Director, we actually have just a first cut on that. We just switched local directors, so I suspect that may have been at the root of some of our demo problems, but we'll find out. But as Bob pointed out, we need to do other devices. We need to be able to manage routers, switches, network storage in order to really be able to deal with a large-scale service. In our APIs and protocols, we have BMCP and the namespace queries. We're still very much in flux as our design is completed. What the team has done is if you consider the architecture of the system a level 0 problem, and then a design document off that a level 1, and then implementations level 2 or 3, we did just enough at level 0 and 1 to do a proof of concept. There was a lot of skepticism that Big could do what it said it could do. Had our demo completely worked, we would have shown you we're doing everything we say we can do. Okay, so we rebooted, waved our hat, burned some incense to the demo gods, and I understand that if I finish in time, we can show you the demo, that part of the demo working. But we still have a lot of work to do. If you drill down on some areas, you'll find that, for example, our group membership protocols still need a lot of work. Nested policy and compound components. Yes, we need to do that. We haven't demonstrated it. Our demo right now depends on a flat infinite bandwidth network. As Bob pointed out, that doesn't scale. So we have some more work to do there. And there's just a list that I'm not going to read for you of things that are still at the design stage. What we're doing is we want to work with the NT team, which we've already begun, to convince them and others that the NT kernel as the beam monitor is the way to go, and hand that off to them so we can go focus on the management system issues. We want to work with D'Souza's team to make sure that they create installation tools that will give us the ability to create and manage images the way we want. And then that's a list of what we have to do. We're going to host the offsite. The NT team has actually already called for an offsite on computing and storage virtualization. I don't know when that's happening yet. We want to make sure that we work with the NT team to ensure that they know all our requirements. And since we're actually developing a prototype of the kernel code to do that, we think we'll be in pretty good shape there. And we need to make sure we work with all the potential users of the big management service to ensure that the scenarios we're creating will manage a large-scale service. And with that, I'd normally take questions, but you guys want to try the demo again before we go into that?
Why don't you take questions?
Okay, well, they get the demo started. I'll take some questions. Yes?
What are you doing in terms of a joint development program, either both with the network equipment providers, routers, and as well as service providers?
So far, none.
Okay.
Right now, as I said, we only have one driver, and that's for Cisco Local Director, and we've just gone through our second rev on that because we got a new local director that was slightly different.
Do you work with Cisco on that?
No, we just use the docs for it.
Cisco knows nothing about this.
Cisco knows nothing about this. This hasn't been disclosed really much outside of Microsoft, and Cisco probably wouldn't like something that turns a load balancer into a generic device where you could just then have this simple API that does the management, addition, and everything for you. But we'd like that.
Let's talk. I'm from NSG, so I'd like to talk offline.
Sure. Any other questions? Yes.
Yeah. First of all, I'd like to say this is really fascinating work, and I'm really glad to see it happening. As somebody who has survived the trials and tribulations of creating an MSN property as a dev manager of Encarta Online for the last 4 or 5 years, there's been a lot of pain growing a site like that. I'd like to make 2 recommendations. You may well be doing this already. One is to live the life cycle of an MSN property. That doesn't just mean like meeting with them occasionally. You should plant one of your researchers right with the team, so that, for instance, parts of MSN research, I've done that before. There's a MSN researcher that actually reports to the search team. Just be there all the time so that you understand all the trials and tribulations that they have. A second recommendation would be, and I'm not sure where the company is on this, but to make it a requirement of an NT service such that the attributes of a warning or an error that is logged in the event logs has a certain number of requirements in it. This will help with your health and monitoring that you were just talking about briefly. Most events that are logged in the event logs are totally cryptic. They're hex dumps of data structures that are of interest only to the developers that have created them. And they're generally unmanageable services. So if there are requirements for an NT service to be created that specify certain attributes of what actually happened in a logical wizard-like, like just embedding a URL, for instance, to a knowledge base of information about that particular service, so that an administrator could respond to it logically and track down that error. But even going much further than that, making it so that the system management tools could somehow probe those event logs and put some of your layers of service description service description SDL language.
One of the things that's become really clear to us is the ability to audit and track what's going on as a part of debugging and managing the service, and even billing in certain scenarios is going to be really important.
So in order to accomplish that, the lower level services that you want to monitor have to meet certain quality, certain requirements.
Absolute sense.
I started to load, and it's growing ultimately, and they're opening up, and you'll actually see that last do that kind of stuff. So I'll just leave it on the next time. If I switch back, actually, I'll actually stop the. If I refresh this page.
One of the things you'll notice is you'll see that there's now a count of 3 backends. Oh, wrong mouse, no wonder. You'll see that there's 3 backends up there now. And it was such a good load that it isn't responding. Okay. You had a question?
A few weeks ago, I was playing around with that center in terms of using its policy monitoring tools. Besides the fact that it's a huge resource hog and unusable in a deployment environment, it did provide a simple way for adding and managing events and actions associated with events. Those events being HTTP performance or event log entries, bird finding, and so on. Do you have any plans for a programmatic model? Well, there's some model in which you can enter those sorts of event types and how to deal with them, and something perhaps a little less onerous, but writing new applications for new event handlers.
I'm not sure how easy or hard it is to write App Center events, but for example, the event that Bassam set up for the demo was a WMI CPU load event, and we just wrapped that to fire off a big event, a big management service event, to tell us that this had occurred. I think our wrappers are pretty lightweight in terms of going around the API.
That we trap. There's no wrapper on top of it.
So, but what Bassam said is all we're doing is trapping the WMI event. There's no wrapper. That's stuff that we certainly need to do in order to finish our model, and that's why we're working with the App Center and Data Center teams, and also with MSN Properties to see what are the kinds of things they need to monitor, what are the kinds of events they need to track in order to do a good job managing their service, and that's all stuff that we need to complete before the service is workable.
One of the notions we have is also this notion of reusable policies. So if there are certain events that are very common, you can imagine a pre-canned policies that you can just plug into place. And for example, an overload and growth event, you can have a pre-canned policy for that which you can just reuse. So we definitely want to look into those.
Yeah.
So is it your intention to move all sort of ongoing status monitoring, health detection, and recovery policy and code to external systems from the end nodes?
No. I don't think we have any intention to move policy in any one way. There's certain...
Well, no, so you've got the machines up, you've provisioned them.
Right.
Now when one fails, somebody's got to detect the failure, decide what to do, yada, yada, yada. And the question is, are you centralizing all of that in a set of management services that run external to the end nodes?
No, not necessarily. In the current implementation, yes.
But where are you going?
There are two extremes, right? One is totally centralized, the other is totally distributed. And I think we'll end up in the middle somewhere. So it's a very vague answer, but
yeah. Clearly we have a systemic problem in all of Windows that you can't assert that at the right level. You want local control, you'd like to be able to come in and authorize it, bring it out to a domain level, or bring it into some arbitrary third-party authorization. We don't have any real good way to do that within WMI or anything else in Windows. And I think the point's well taken that you could easily see a system like this running with one admin, and all of a sudden 3 machines goes down, and he's busied out trying to figure out what to do because you can't assert and take control and know what level you want to be.
Ideally, if 3 machines go out, and we've done a good job with the policy, the admin just has to watch. I mean, you could have it so it fired an event, but the admin console didn't do anything until they approved.
What if IIS? What if the IIS process fails?
Kill the machine.
How?
You reboot the machine. You start another one.
Okay. How do you know it failed? What is your policy? The IIS failure level says this is what we do when this happens.
There's a number of interesting ways you can monitor. Like you can look at, for example, if you know that a front-end box is supposed to render 100 pages per second, for example, as a monitor.
If your load is very light, that's a funny number.
No, I understand, but looking at load, looking at things that the machine does, which are very app specific, right? It overrode a buffer log, or it did something really funky in the app. Then you could actually imagine sending events or reporting these things. And somebody like a policy engine, or locally, the machine decides to reboot itself.
All I'm saying is that we in our Windows environment don't have good ways of aggregating and analyzing those things either statistically or in patterns or rules and determine and it triggering behavior that's predictable.
One of the reasons that we feel we have to deal with some large-scale services like Passport, Hotmail, and Exchange is because just to find out what all these things are and what are acceptable levels, we could go around in circles forever. The only way you really close something like this down and get a version of something out is by getting customer requirements, which is why we're doing that. Yeah.
Does this work result in the option to boot an in-memory only version of NT?
No, not a full in-memory only version of NT, but our in-memory B monitor is something you can boot.
Just a command line environment.
Well, it's not. I mean, it doesn't have the full Win32. It has the kernel APIs, and it has some drivers for dealing with the disk in the network.
Doesn't have Win32. No Win32.
No Win32. No. There's lots of no. But what we want to try and do is get enough so, as Galen was saying in his part of the talk, the machine is always manageable and always accessible, so that you could imagine a policy set up so that, the machine isn't responding to a heartbeat anymore. So you could have policy just say, to heck with it, I'm going to reboot it, and it's going to keep track that it rebooted that. And if the reboot doesn't work, it just takes that machine out, prints off a work ticket. Somebody's got to go pull this machine out, slap a new one in, and check it, because it could be any one of multiple failures. Or you could imagine policy where it always alerted because you're a smaller service and you can't afford to keep pulling machines offline. It's going to be very specific to the app and the service, and there's lots of ways we can attack it.
There's another useful reason for having NT be the B monitor, which is that there are a lot of APIs that allow us to, say, partition the disk, format the disk, move files on and off the disk. So to deal with the registry, and we were doing all those by hand in the old B monitor, and now we have all the real APIs for it. It's a very nice way of abstracting those things.
Yes.
So I mean, as I look at this, I've stolen lots of stuff from Robert O'Brien. He's a really good guy to steal from, and a lot of his latest stuff has, if you're just using a compact insight board or some out-of-band management options, a lot of them, and you're doing a SIF, doing a sysprep, that stuff, the VMON stuff, the work you're talking about, the low-level drivers and other stuff, in the data center builds that we do, we've already solved that for the server with the lights out board. It doesn't work in your machine there for Hotmail, but it works in most of the other data centers we built because they're compact. So the interesting piece is the resource management piece to me. I guess my question is, I know vendors haven't been involved yet, but is it a more interesting, or is it maybe a parallel development path to see if we can get some vendors working on the BMON piece so that they can embed it in their hardware, whatever that is?
The whole idea behind doing the B monitor this way is that we rely on Pixie, which is already standard, already embedded in hardware. We don't have to get into the business of telling people, this will work if you just run around with a diskette and reflash all 3,000 of your machine's BIOS. And it also, we don't have to go to the OEMs and evangelize, gee, if you'll just do this, because they're already doing Pixie. So we're trying to do, and what we've done, we believe, is found a way to leverage the work that's already been done to get OEMs to ship certain types of machines. And then we can go work on just the software piece.
So the goal then, again, I saw it fixed there, but I wasn't sure. Life cycle is to get this out of flashing it to a network card or to a motherboard.
No. The way this works is Pixie boots. When Pixie comes up, it goes out and looks for a DHCP server. That's how we find it. And then the DHCP server says, you go here to get your code, which brings down StartROM. Okay? StartROM then goes out to runs some detection, tells us what devices are on there, brings down the NT kernel, and then the RAM file system that has the drivers and some registry hives, and it just boots. So we don't have to have anything else.
I'm aware of Pixie boots. My question is, though, that and just from a level of effort, I'm trying to figure this out. The interesting stuff to me is the resource piece. Just for me to say,
what do you mean by the resource?
The Visio resources define says go out and look at that device and get it configured. I'm just asking, is the VMON piece required for that, or is there another way to solve it that already exists?
The problem with the existing stuff is that we're already running into it. I just met partners the other day, and that's a brick today, but we've got people doing bricks a lot smaller than that. So adjunct boards that support out of band they're dead in the water. So
one of the things we talked about, a device driver model. Okay, the B monitor is a driver for us in that respect. And so if vendors wanted to sell these extra management boards, okay, like Compaq and Dell have, they could write a device driver that would plug into the big framework and use their hardware mechanisms to reboot the box and to do those. Okay, so it's just a device driver for us.
Okay, I think your work is great. I think it's cool. I'm just I'd like to use it like next Tuesday.
Yeah.
That answers in a sense, answers your question. What it says is, if you have a device driver right on, say, your Compaq box, you don't need the B monitor NTVM to work in the larger management service.
Yeah.
Right. Just like the Cisco Local Director, we have a driver for it. It obviously doesn't run NTVM.
So from the IT perspective, the site operations where the physical world gets, having another connection is getting unmanageable. We've really hit the wall of the physical wiring inside the rack. So the one power cord, one network attached is the right way to go. Right. And I see also in the future that possibly get SAN connectivity through the network fabric. That could be a way, right? So the end switch is now beginning to become the speech-to-speech router, right? We're seeing that too. But so we've moved the center of the known universe from the PC bus out to the patch cables, right?
Right.
So now we've introduced, that's our weakest link in our data centers, right? It's a mess. Okay, so we can clean that up by moving that switch closest to the PCs, okay, and harden that up a bit, and then later on get that into, say, a switch fabric, or almost starts looking like the backplane of a router or a catalyst switch. That's probably where we need to go from a hardware. But what we're saying in IT is we got to take all the physical problems that we're having and make it a software problem. So it's the direction that you guys are going are right in line. Okay. One of the things I might suggest is adding the site operations and the global operations of IT to your customer requirements list. Just as like you're working with NSG and the Exchange side, because we're wrestling with all these problems and how to build a next generation data center, and we have so much data on. We've hit the wall.
Yeah.
And like dealing with power. I mean that's another issue right now. Is 10 kW per rack. Okay.
We have some crazy ideas about power, but
yeah. So do we.
I saw some stuff from research on a distributed file system that handles backup.
That's talking about Farsight?
Perhaps. Is that something that you think plays a role in what you guys are doing, or is it?
I mean, it could, but it isn't required.
Farsight's got sort of a different design point because it's trying to aggregate untrusted storage servers, stores, and create reliable private storage. So it actually has a little bit of it has quite an overhead to maintain the trustedness that we don't think is really central to.
But it totally fits in our framework.
Yeah, it could. Yeah, I'm not sure it would be competitive with simpler storage mechanisms that don't require the level of security and the level of lack of trust that they operate under. But you should talk to them instead of.
Yeah, I mean, the idea behind Farsight was to try and create loosely created networks that were reliable and with mutual distrust. We're not getting into that in our design right now. Good.
I may have missed this when you talked about it, but when you have a machine up and running and you want to repurpose it, do you have a way of downloading that or trickle down that image before you do the reboots?
That's what we
not right now. That's what
we don't do that now.
So we actually want to do it in the background as well while the machine starts.
So a service backer, any kind of upgrade requires a complete reboot to
right now.
Yeah, right now, yeah.
Okay. So have you guys looked at Altiera's? Have you looked at their delivery mechanism?
No.
So they deliver a sysprep image, and then while the machine's running, have an agent in the background take the deltas, and they've got tracking. It's called Altiris. It used to be lab deploy and wrap deploy, and it's gone through many. But a couple guys from.
Yeah, there's actually a bunch of really cool tools out there too. You can look at one called Brembo.
I'm just looking at tools that exist today that operate more code.
I mean, there's lots of possibilities. One of the biggest problems we have is taking, okay, gee, let's look at all the different possibilities and narrow it down to what do we need to do to get a workable version 1, which is where that focus on a few deployments comes from. Because we could really something we could start designing version 3 already, or everything you want in version 1.
How do we get, before the offsite, how do we get enough of your stuff to play with it to give useful feedback? I mean, what's the...
Play with, I mean, well, what you saw, it's pretty fragile stuff, right? There's nothing there's our website, which is HTTP Dig, and that's where we posted everything for people to check out.
The audience.
It's time to go eat lunch. Thanks, everyone.
Thank you.